volunteering to bring people to Des Moines, also to talk to Paul. I think there are a couple of persons that have cards. Okay, so let's continue with the second lecture by Ricardo Nochetto on numerical analysis for fractional non-local PDEs.
Thanks. Well, as I said yesterday, this second talk is going to focus on another definition of a fractional Laplacian, so-called spectral definition, because it uses spectral analysis and spectral decomposition. So here's a plan, more or less along the same lines as yesterday. I will tell you about the definition and a few properties. I will focus a little bit on regularity. Remember, regularity and approximability are two sides of a coin. And then I will introduce the error analysis, the first step that we have done a few years ago, and then the more recent work, 1 month old, this is very recent, and then a posteriori error analysis and conclude. So that's the plan. Okay, so here is the problem that can be a study with this formulation. I will be considering the domain which is bounded. The boundary will be Lipschitz. Typically, it will be a polyhedral domain in any dimension. The operator can be of this form, symmetric, self-adjoint, with maybe good properties on the coefficients A and C. And we would like to get fractional powers of this operator. Everything I will say applies to this operator, provided A and C have decent reasonable assumptions. But I will focus on, again, the Laplacian. So everything I will do for the presentation to simplify things will be for the Laplacian. So, and I want to stress now, because I will say no more about that the two definitions have been studied. The connection between the two definitions have been studied recently by Caffarelli and Stinga. Okay. So here is sort of the key transparency regarding the definition. The operator, say the Laplacian or the general L, we can view as mapping H2 intersection H10, the domain of the operator, into L2. And because it's certainly symmetric, closed, and bounded, and the inverse of the operator, going from L2 back, is compact. And the fact that the operator is compact allows for spectral theory, in particular the existence of eigenpairs that we call lambda k phi k, a countable number. The eigenvalues are strictly positive, and in fact the eigenfunctions form orthonormal sets both in L2 and in H1, and I will normalize them in L2. So once you have that, then you can write, at least formally, assuming the function u is smooth, you can write the function u, well, for this you need only the function to be in L2, as a series in terms of eigenfunctions, and the uk are the Fourier coefficients. So if you formally apply the Laplacian to this left-hand side, and a hit with the Laplacian on the right-hand side, you get the Laplacian of phi k, and that happens to be the lambda k phi k, so you get this representation if s is equal to 1, okay? The Laplacian of u can be written as a series of, the coefficients are lambda k uk, in terms of the eigenfunctions phi k. So it's a natural thing to do when you want to go in between powers in between 0 and 1, s powers, to define, this is the definition of the fractional Laplacian, to raise the lambda k, that for s equal 1 will be power 1, to the power s. And that's the definition, the so-called spectral definition. This is not the same as what I did before, in the last lecture. And the discrepancy between the two definitions comes in several flavors. In particular, the behavior at the boundary is crucial. The boundary of the domain, the behavior is different, and this will be something I will say in a moment. Remember yesterday the behavior at the boundary determined the rate of convergence. So that will play a role also now. Okay, so for the Laplace operator, the natural variational setting is, h1, h minus 1. So here is the natural setting. The operator maps hs into h minus s. Remember, this hs is something, this symbol meant something yesterday, which is a regular space hs, but functions with functions that vanish outside omega, hs of Rn. It turns out, even though I will not use this, but this is also something that came up in the discussion yesterday, the space can be characterized like this in terms of the the Fourier coefficient. So our functions can be represented as a series in terms of phi k's, but this series must be summable. This coincides with these usual spaces, hs, between 0, for s between 0 and 1/2, when the s is strictly bigger than 1/2, is the so-called space hs0, so intersection of hs, traces of hs equal to 0, or if you want, interpolation between h1 and L2, h10 and L2, and for the middle case, s equal 1/2, this is always an exceptional case. This is a space so-called Lyons-Magenes. It will not play a role, so I will not insist on that. Okay, so let me present this transparency for those that are not familiar with the extension. Perhaps this is useful. It's very, very well known. It's about to view the Laplacian to the power 1/2 as a Dirichlet to Neumann map. So imagine that we have the following situation. We are given a function u, little u, in Rn, and we solve the harmonic. We want to find a harmonic function, so Laplacian of u equal to 0 in the half space, whose trace here on the bottom is little u. Okay. Once we find this function, cal u, we compute the normal derivative, the derivative with respect to y here, minus the normal derivative with respect to y on the bottom. Okay. That's the Dirichlet to Neumann map. Suppose now that you apply again this construction, but now the trace is the normal derivative of the previous solution. And you apply again compute again the normal derivative, so you again compute the Neumann map. So that is computing twice the derivative with respect to y of the solution u, the original solution u. And because the solution satisfies this harmonic, say up to the boundary, this is the remaining part, the Laplacian in the tangential variables, which I call x prime. Okay? But because now we are here on the bottom, this is the capital U is a small u. So you see that the square of this map, the so-called Dirichlet to Neumann map of a function u, gives you the Laplacian of u. So if you compute the square root of the map, this is a natural thing, this is the square root of the Laplacian. So this is something well known. And this is written here. The key for this, I think, in my opinion, for the development of this theory of fractional diffusion, fractional Laplacian, is that this idea, this extension idea, can be viewed as a particular case of this more general extension. Let me go back already to the bottom. The original idea by Caffarelli and Silvestre was developed in RD. So now we have the whole RD like in this picture. I will use the idea for a bounded domain. Okay, and this was developed a few years later. So here you have a few people that work on that. So what is the idea of this extension? So again, you have a domain now omega, and you want to define the fractional power of u equal to a function f. Okay. So what is the meaning of this? So you extend this problem. This is an infinite cylinder in an extended variable I call y. The cylinder I will call C, cal C, is a product of omega times 0 infinity. So it's an infinite cylinder. And in this cylinder, you solve an auxiliary elliptic equation with variable coefficients. You see there is a coefficient here, y to the alpha. And, well, the value of alpha is written here is 1 minus 2s. This you had to find out, but this is the contribution by Caffarelli and Silvestre. If you look carefully, this alpha happens to vanish when s is equal to 1/2. Okay, that's a special case, as always. And then the equation that you are solving is the divergence of the gradient, which is exactly this problem. That's a case that we knew for many, many years. The new contribution is that this is embedded into a general family of extensions where there is a parameter alpha, and this ranges for s between 0 and 1. And the condition that we had to, once we find this capital U, or cal U, we had to compute a conormal derivative, which I call like this. It's a derivative nu alpha, which you can view like this, computing the derivative multiplying by a certain factor y to the alpha. That would be an alpha derivative of the function. Actually, 1 minus alpha derivative of the function. That has to be f, properly scaled. This ds is a constant you can see here. It's explicit constant. So the contribution in this by Caffarelli and Silvestre was to formulate this problem, and in fact to realize that once you solve in the extended domain and you compute the trace, you get the original function u, provided that the problem satisfies that the conormal derivative is equal to the force in f. So you can go from here to one more extension, to one more dimension, and back by taking the trace. Okay, that is a key tool introduced years ago, and it was fundamental to do, I think, as far as I know, to do regularity theory of problems associated with the fractional Laplacian. The reason is that this problem was hard. It's an integral equation, to some, at least in the whole Rn. This is a PDE problem. It's a local problem in one more dimension. So PDE tools are accessible, and it is a natural thing to try numerically the same thing. As I told you yesterday, the integral formulation is complicated. It's complicated to compute the integrals. It's complicated. You get dense matrices. You have to deal with issues that are delicate from a numerical standpoint, even at the level of implementation. Not to talk about the numerical analysis. If you now have a PDE, maybe in one more dimension, you have to pay for the additional dimension, but you have something that in principle you can access with PDE tools, and we know how to do that. So the idea that we can use this from the numerical point of view is appealing. And that's what I want to tell you, what we know about it. Before I do anything, since I had to speak about regularity, let me anticipate that this is only wishful thinking. There is a principle of conservation of difficulties in all of this. One difficulty is that I have one more dimension. But nobody tells me that this is a good PDE, that it has a good behavior, and that I can approximate it, give it to somebody, go to sleep, and the morning after I have something. I had to convince you that there are issues associated with this problem, and these issues are the ones we had to address. But we are getting around the integral formulation. And the question is, does it pay off? What do we get out of it? Okay? Numerically. And that's what I want to discuss today. Okay. Here is again the same view. This is as a picture. You have something in the domain omega. This is the extended variable. The solution of this problem, the capital U, it certainly has a lot of activity. Something interesting happens on the bottom, but as you go up in y, the function decays. And I had to be precise about that. I had to quantify the decay. So you can see here, this is the y. This is the y variable. And you see that the function decays quite fast. So again, the problem is the fractional diffusion, the fractional Laplacian, but for all of what I'm going to say today, this will be my problem. It will be in one higher dimension, and the solution will be this capital U, and I will get the little u by taking the trace of that, okay, on the bottom. There is an alternative formulation using the Laplacian formula that is written here. I will talk about tomorrow. Okay, so what is a weak formulation? If you think about it, I have a divergence type equation with variable coefficients. So the usual thing we do is to multiply by a test function, integrate by parts, and see what are the natural spaces. So this y to the alpha just comes up as a weight in the usual Dirichlet integral, the integral of the gradient. Now we have a weight y to the alpha. So it's natural to define this space, functions in L2 that are in L2 with weight y to the alpha, and the gradient is in L2 with weight y to the alpha. All in the cylinder, remember, omega times 0 infinity. But I want the function to vanish at the lateral part of the cylinder, lateral boundaries, meaning here on the lateral part, this part and this part, the functions will vanish. Well, all of this for the moment is formal. I'm not sure that this makes any sense. So I had to speak about this, whether it makes sense. And here you have a picture of the weight, y to the alpha, for different values of alpha. For alpha equals 0 is constant, but as you see, if alpha is positive, meaning s is less than 1/2, the weight degenerates at 0, it becomes 0. If alpha is bigger than 0, and so s is less than 1/2, the weight blows up. So you have the two behaviors at one depending on s. You have either degeneracy or blow up. The weak formulation, as I said, is obvious. We integrate by parts with the test function, and this is the bilinear form that you would get by integration by parts. And this would be the way to speak about the conormal derivative. It's just a Neumann data that appears in a natural way. F is the forcing term, remember, in the problem here. ds is a constant, and this is the trace of the test function. I had to make sure that the trace of functions in this space makes sense. Okay, but that's the formulation. And what I want to say is a few words about the formulation, about the regularity of the solution, and then the associated numerics to it, method and analysis. Okay, why does it work? Why is this a correct formulation? Why do I have traces? This is all related to the fact that the weight, y to the alpha, is a one instance of something more general that are called Markov weights. And in fact, it has this, I would call it non-oscillation property. That's what makes the weight good for PDEs. So you take the mean of y to the alpha, normalize, and then you take the mean of y to the minus alpha and normalize. I told you that the weight y to the alpha can go to 0, and in that case y to the minus alpha will go to infinity, or the other way around, depending on alpha. So this can go to 0, it may be small, but then that will be big. The question is that if one is small, the other is big to compensate. And there is a universal constant, so-called Markov constant, that bounds this for all A and B. This is a property of Markov weights in class A2. And this y to the alpha satisfies that. Because of that property, then there are many consequences. For instance, Hardy-Wellitiput maximal operator is continuous in L2. And that is good for PDE theory. Singular integral operators are continuous in L2. And in fact, for properties like this, the Markov class is the largest one. You cannot weaken this much more than that. Y to the alpha is one instance of that. L2 is embedded in L1 log. H1 with weight is a Hilbert space and functions with infinity with compact support and dense. And traces are well defined. So all these properties are consequence of this, and in fact applied to our case. Okay. And we have a little more. we have Poincaré inequalities like this. This is not difficult to prove. So the L2 norm, remember the functions that I'm dealing with, these functions, because of the 0 on top here, means that they have 0 trace on the lateral boundary. Okay, so this is a natural thing. The L2 norm is controlled by the gradient. You cannot raise a function without changing the gradient too much. But there is a weight, the natural weight, y to the alpha. The trace operator is surjective. Remember, it will take functions in this space, in the whole cylinder, functions in H1 with weights. I compute the trace on the bottom, and that happens to be an HS function, and this operator is surjective. So I get all the space. And, well, because of all these properties, you can formulate the weak formulation here. You can study the weak formulation with the simplest possible tool, Lax-Milgren, and that will give you a solution. Okay? Now, what about the regularity of the problem, which is important to understand for the numerics. So let me address that very quickly. So here are some basic tools that we use for understanding the regularity. So there are two things that I want to tell you: is the regularity in the x prime variable, so meaning in the variable in omega, and then in the variable y, in the extended variable. So it turns out that you can write the capital U in terms of a series where the phi k's are the eigenfunctions of the Laplacian I introduced earlier, and the psi k here happen to be solutions of this two-point boundary value problem, which is associated with Bessel equations. Okay? In fact, if Ks denotes is a modified Bessel function, second kind, the lambda k solution of this problem is a rescaled Bessel function with a factor in front. Okay, this is something that can be checked. Bessel functions are well understood. This is one of the key special functions, so we know a lot of properties. In particular, what happens when the variable goes to 0 and when the variable goes to infinity. So behavior near 0 and behavior at infinity. In particular, when you put it together, you see that the function psi behaves like this. The function here that you use to expand the solution in the cylinder has a derivative that blows up like y to the minus alpha, and the second derivative like y to the minus alpha minus 1. So the solution, the psi behaves in a way that every time you differentiate, you lose a y. Okay? So in particular, the derivative is already singular at the origin. Okay, and when you look at the behavior at infinity, you see there is a power here, but it's exponential. So it decays exponentially, which confirms the fact that the solution of the problem has a life close to y equals 0, but then it decays fast. And we are going to exploit that. Okay, so here are simple facts. Okay, this is not deep at all. You have to put it together using this representation. So for a large part of the talk, I'm going to assume that the right-hand side, f, is in H1 minus s. So let me pause and make a comment. So suppose that s here is bigger than 1/2. Okay? So then the exponent here is less than 1/2. So this is a regularity, a fractional regularity of f, but it doesn't impose anything on the boundary. The function 1 would be in that space. Now if s is less than 1/2, this will be bigger than 1/2, and then I want to impose that the function has a trace equal to 0. Not all the time. I will remove that assumption for the moment. So I will call that compatibility assumption. It's a compatibility of the data with the boundary. That will lead more regularity. If we don't have that, then we have to pay with the behavior at the boundary that I will mention in a moment. Then you can get results like this. These are equalities. This is just playing with the equation. Okay, you can control of the Laplacian, control of mixed derivatives in terms of this regularity of f. You have regularity in the extended variable. For instance, you can estimate two derivatives. Okay, but in order for this to be bounded, you need to increase the weight. You see the beta, the weight for y is now going to be much worse than y to the alpha, in the sense that it has to go to 0 to compensate faster. Okay, and if I have what we call elliptic regularity, for instance, for the domain convex, we know that the Laplacian of the function in H2 controls all the Hessian in L2. With that assumption, say for instance on convexity of omega, because we have control of the Laplacian, that will provide control of the full Hessian. I will remove this assumption later, okay? This assumption is just for the moment, so the convexity is a convenient assumption for analysis, but not realistic. Okay. Now, back to the regularity I mentioned, this is a rather recent result for the fractional Laplacian with the spectral definition by Caffarelli and Stinga. The behavior of the solution, now I'm not assuming anything on f except for regularity. F, I mean, it doesn't have to be compatible. It's like a power to the boundary, power 2s, if s is less than 1/2. For the integral operator, the power was distance to the s. So this is a smoother problem. In fact, when 2s becomes bigger than 1, so s between 1 and 2, then it's a distance to the boundary, it's a smooth. And then there is an exceptional case. The s equal to 1/2 is always exceptional. You typically pay with a log. So that's the behavior when there is incompatible data. Smooth. Okay. And now, this is more recent. It has to do with analytic behavior. You will see why I want to care about that. This is analyticity with respect to the y variable. So you start computing derivatives in y, because you have explicit formulas. Solutions of this Bessel equation you can sort of compute, and you can go up with the derivatives as much as you want. You start seeing a certain behavior with factorials, and that's the typical thing, because you have control of these things that provide some analytic regularity. Here is more precise. You can control any derivatives in y, provided you put certain weights. So here is the weight. You see, you had to put a larger weight in y here, and then you see a behavior on the right hand side, how it depends on L in factorial, and the regularity of f is the range of nu. You see, can go from 0 up, so you can be h to the minus s if you don't involve x prime. If you involve x prime, then you have to start, maybe there is a 1 here, I'm not sure if this is correct. Anyway, so those results will come up later. This is very recent, and I will show you why we need this. Okay. So now, how do we deal with the domain? The domain is infinite now. It's an infinite cylinder. We have to truncate the domain for numerical purposes. So we start with the domain C that is omega times 0 infinity, and I want to truncate at a certain height. I call the height capital Y. Is this cal Y? And because of the exponential decay that I mentioned earlier, you have, if you look at the tail, what happens from capital Y to infinity, that decays exponentially. Okay? So I'm going to truncate at a certain Y, and I'm going to keep the Y as a numerical quantity that I'm going to select at some point. Okay? And I'm going to discard the tail. That will be small, exponentially small. Okay? So you have this exponential convergence between the true solution all the way up to infinity and the truncated solution. This is the truncated problem where now we are setting a condition at capital Y. So now we have a finite cylinder. On the lateral part we want the function to be 0. On the top we want it to be 0. And we discard the tail. And the error that we commit is exponentially small. Lambda 1 is the first eigenvalue of the Laplacian. That's the one that governs the dominant term. Okay. So now let me speak about the numerical method and what we can say about it. Because of the behavior of the function capital Y in the capital U in the y direction, we are forced to use meshes. This is omega in one dimension, and this is y. The meshes that we use, the partition of our cylinder, cannot be uniform. Because if it is uniform, we will be paying a very big price for the singularity at y equal to 0. So it's a very natural thing to have meshes that somehow capture the singularity. Okay, and these are so-called anisotropic meshes. So it's a question of dealing with this singularity that I mentioned earlier. Okay. However, the way we do the meshes is by always it can be a radical mesh or a geometric mesh. The point is that if you look at two consecutive integrals anywhere in this partitioning y, the ratio between the size of the intervals is bounded. That way you can go very quickly, reduce the size very quickly, but consecutive elements are comparable, and this is critical. And this size, the size of the elements in y, is not related to the size of the elements in x. So you will get maybe a very elongated elements. And this is a natural thing to do, but this is an issue that leads to a lot of trouble numerically, because we are violating what we call shape regularity. The domains are no longer like a cube, and we need to address that. Okay. The finite element method is the usual. Now we come up with a space which is continuous functions that are restricted to elements are say P1 in linear in the space in x prime and linear in y. Okay, elements in x are called k, elements in y are called I. The functions vanish at the lateral boundary and on the top. Okay, this is a subspace of our energy space. So we restrict the problem to a subspace and we get the Galerkin solution. So it's the same formulation as before. We are searching for a solution in the subspace and testing against functions in the subspace. It's the same problem. This is the usual finite element formulation. And once we have the solution of this problem, which I call a capital V, solution of this problem, I take the trace on the bottom and I call it U. And that will be the approximation of the original little u. Okay. And as it happened yesterday, we also have a Quasibest approximation result. This is based on projection. I'm using this inner product to project. So if I measure the error in the energy induced by this inner product, the Galerkin solution is the best approximation. And so if I want to understand the error, do the error analysis, a priori error analysis, what I need to do is to understand how well I can approximate the solution of this problem, of the truncated problem, the solution of this problem with the finite element space. Okay? And that's what I'm going to do now. So let me go very quickly. This is a bit technical. So this is y, the variable y, this is the variable x. Here in this variable we can have many dimensions. So say I'm doing RD times R. And this is a node, typical node, and this is surrounded by elements, okay? And say this, if you look at this element, T, this larger set is the element that surround T. I'm enlarging by a ring. So now the question is the following. You give me a Markov weight, say y to the alpha. What I'm telling you here is not restricted to y to the alpha. It's valid for any Markov weight. And if in that respect is new in the approximation theory, because people never care about Markov weights until they have to do it. Like, okay, this was not done. And in fact, it is interesting because you cannot repeat. It's not that you put a Markov weight and everything works. I will say a couple of things about that. So the way we do these things is by averaging, okay? This is typical in the finite element literature. So you compute your average Taylor polynomial. So you get the function, so you get a function phi in some LP space. And pretend for a moment that the function is smooth. And you write your Taylor expansion of the function phi, written here up to a certain order, and multiply by a cutoff, and integrate. And this gives you a function, a polynomial of degree m, evaluated at y. This makes sense. It's a sort of averaging of the Taylor expansion, so you are missing a tail of the function, provided the function is smooth. But your function is not smooth. So now you look at this formula, because it's a cutoff function with small support, you integrate by parts, and put all the derivatives that you have here on these terms. Of course, if the function is smooth, it didn't change anything. But if the function is not smooth, you have now a representation that you can extend to any LP function. And you start from there. This is a way to do Taylor expansion with an averaging. So you don't need point values. And with that type of polynomial, then you want to do a certain error analysis. So you need to deal with this, I don't know, Bessel potentials. And that's where the problem starts. Because the usual thing, when you don't have Markov weights, it's not difficult to handle this with techniques from real analysis. But when you have the weights, these things don't work. So we had to come up with alternative ways of proving that this is small. And this is based on Poincaré inequalities that we had to prove. A function minus a mean has to be bounded by the gradient times the size of the element, but on Markov weights, with Markov weights, and then an induction argument that uses Poincaré at every step, and it reaches every possible polynomial degree. This is not the usual proof. Anyway, with this theory, we can now, because we have these polynomials, okay, given a function v, which is LP, you have a polynomial of degree m, let's say, degree 1 if you like. So you look at a node, and then you have a polynomial defined near a node, with all the values of the function nearby. So you can evaluate this polynomial at a vertex, at a node, and that gives you a value of an interpolant, which I call pi of phi. Remember, given a function, I want to construct, say, a piecewise linear interpolant. The Q that I define here is a polynomial, say a linear polynomial. That is only a good approximation close to a point where I'm doing the averaging, so close to the point y. Excuse me, close to the point x. If I go far away, I'm not getting a good approximation. So what I do is I do an approximation next, close to a vertex, to a node. That gives me a polynomial, and I evaluate the polynomial at the vertex. And that gives me a nodal value, which I call pi of phi. And then, given the nodal values, think of piecewise linears. I have triangles, I have nodal values, then I extend by a linear, and I do that everywhere. So the difference with the usual construction is if you give me a function, I'm not evaluating the function at a node, and I declare that to be the node, the nodal value, because that doesn't make sense. I do an averaging that has high polynomial degree approximation, and then I evaluate that. And then I extend with polynomials. Okay, so that's a regular construction, except that now we have to do it with weights. All right. And here you have a list of properties. And an important property that we had to face, and that's something I want to stress, is that if you do this construction and you pay no attention, when you look at the difference between, you see here, the difference between v and a polynomial, and you look at a derivative, the derivatives usually mix. You don't get a clean separation. You don't get a separation of derivatives. So it would be nice, interesting, that if you look at this thing and you differentiate with respect, for instance, to one of the variables, what you see is the regularity of the solution in that direction, and that you don't get mixed regularities. Because remember, I have to deal with anisotropic meshes to account for the behavior in y. And if I'm close to the bottom, the elements are going to be very long in the x direction and very short in the y direction. When I measure in this direction, I like the regularity in that direction to pop up, and not something mixed. And when I measure in this direction, I like the regularity in this direction to pop up. This is non-trivial, because I'm not dealing with, this is not one-dimensional, this is n-dimensional. So the separation of approximation is a non-obvious property. It turns out that this can be done, so you can separate. For instance, if you look at derivatives in the j direction, you can see here, you approximate, say, derivatives in one direction. It involves derivatives in that direction and derivatives in any other direction. But here you have the h that appears, the I that appears, multiplies the corresponding derivative, okay? So this type of thing is crucial. If this derivative, say the derivative 1, 1 is big, you are multiplying by h1, and then you can compensate with the small h1. Okay? All right. By the way, I'm not sure I mentioned the people. These ideas here are based, the modifications of tools that were developed by Duran and his group. Okay. All right. So this is again the same transparency about regularity I mentioned earlier. If you look at the solution, capital U, the derivatives in y, two derivatives degenerate this way, and then you have this regularity in x and xy. Okay. So in particular, the U, as I said earlier, does not belong to the space H2 with weight y to the alpha, but rather you have to increase the weight to the beta. All right, so how realistic is all of this? So suppose that you want to try uniform meshes or quasi-uniform meshes because, you know, the theory may be too pessimistic. So you go for quasi-uniform meshes, which I advocated to be wrong, okay, earlier on. If you do that, your analysis using these estimates that I just mentioned, interpolation estimates, give you that for the energy norm, and as a consequence, by taking the trace for the trace in HS, give you all the HS minus epsilon, for every epsilon. This is quite pessimistic. Remember, we have linear functions. Okay. This is suboptimal. And in fact, if you look and if you do an experiment, this is a simple experiment in one dimension, that's what you see. So the theory is sharp. If you don't do something in the y direction, you have to live with this rate, which is quite poor. And that's why we want to do anisotropic meshes. So if you do anisotropic meshes, you need to grade the mesh. And here is one attempt, the first one that we came up with in 2015. It's a radical mesh. You see, you scale. You see the yj is j to the gamma, and gamma is a certain quantity bigger than 1. Then you need to tune to equilibrate the errors. Here is a value for gamma in relation with alpha. If you do that, this requires some calculation, which I'm not doing. Your error estimates in terms of h being the largest h. Okay, say the h that you will have in the x variable. It goes like this. It was h to the, remember, it was h to the s, basically. Now it becomes h up to a log. But provided that the function u has this regularity, h1 plus s. So from the point of view of regularity and order, this is optimal. You see, you have the regularity of the solution in h1 plus s. You measure in hs, so you expect the rate here to be the excess, the difference between this Sobolev number and this Sobolev number, 1. Up to a log, because remember there were epsilons everywhere. So that accounts for the log. In terms of degrees of freedom, you can write it like this, where I'm talking about n to be the number of degrees of freedom in the whole cylinder. This is a fair calculation. In order to solve this problem, I need to solve in a cylinder, and I need to have degrees of freedom in both x prime and y. If n is the number of degrees of freedom in the entire cylinder, this is the behavior. Okay? This bound and this bound are equivalent because of this relation. So this is a simple consequence. This is nearly optimal in terms of regularity, and if you want decay rate, but it's suboptimal if you measure this in terms of degrees of freedom. So if you measure in terms of degrees of freedom, we are thinking about complexity. How much do I need to invest to get a certain decay? And I need to invest in degrees of freedom that scale like this. If I look at the number of degrees of freedom in omega, which I call n omega, the total number of degrees of freedom, this, is a little bigger than omega. It's 1 plus 1 over d. Okay? So it's not optimal in terms of complexity. The experimental rates of convergence, here is an example in 2 dimensions, show that you do get what the theory predicts. So in 2 dimensions, you expect decay 1/3, in terms of degrees of freedom, and this is what you get, both for s equal 0.3 and s equal 0.7. So you get what the theory predicts. The theory is sharp. But we get a suboptimal behavior here. And that was the situation, you see, a few years ago. And this theory assumes that we have compatible data and that the domain is convex. So we are taking as much as we can, and still we have a suboptimal method. Is that something that is unavoidable, or somehow we can cope with, we can compensate one way or the other? Okay, and that's where these tensor product finite element methods come in. So it's an attempt to, let me go back, in this formula here, get that the total number of degrees of freedom behave like the degrees of freedom in omega, basically. That I do not increase too much the number of degrees of freedom in omega. How can I do that? Basically by being very selective on what I add in the variable y. Okay? I cannot just add things liberally, because otherwise I pay. I have to be selective. And that comes in several flavors. I'd like to tell you 3 options for that. Let me start with an observation that I find particularly interesting. We call it diagonalization. Suppose that I have in the variable y a certain mesh, which I call GM, with m intervals, any mesh. Okay? I partition this in some way. I have m elements. Maybe this is going to be graded at the end, but for the moment it's anything. But in the variable x prime, in the domain omega, I have a continuous problem. So it's semi-discrete, discrete only in y. Okay, and I look at this semi-discrete problem. So continuous in y, in x prime is h10, and a space of elements, piecewise polynomials of degree r, let's say, in the mesh, continuous. So say piecewise linears in y, that h1 in x prime. And the solution I call um, to recall that m is the number of degrees of freedom in y. Then you look at this eigenvalue problem. Okay, it's one dimensional, it's to take care of the variable y. This is an eigenvalue problem with a weight that corresponds to the problem in y, not in x. Because the solution of this problem is a polynomial in y, and is an h1 function in x prime, you can write as a sum of, n terms, let's say, of functions in x prime, okay, which I did here. The solution of the problem is a sum of certain functions and then a basis of the space in y. The basis I can write any way I want. For instance, piecewise linear but I can also try to find an eigenvalue decomposition, eigenvector decomposition. So now I put here eigenfunctions, which are solutions of this problem. Now if you do that, this problem splits. It splits into problems that are decoupled, and these problems are written here. For each of these functions satisfied an elliptic problem, which is singularly perturbed. These mu's are the eigenvalues of this problem. You see they involve the Laplacian and a L2 term. They are singularly perturbed when these mu's become very small. And the right-hand side is the value of the function, the test function at 0, and the function of the value, of the eigenfunction at 0, the b, and f. So we have a sequence of m decoupled problems. So now if I want to solve in the whole, this has several possibilities. Numerically it can be used to solve a problem. Because now if I want to solve a problem, the full problem, I need to discretize in x, which means I need to solve these problems discrete in x, which means I need to solve these problems discrete in x. But they are separated. So they can solve them in parallel. Now I don't have to deal with the variable y. I don't have a coupling in the y variable. I can solve n problems in y. Okay? And these are the involved operators that I know. These are regular things that we know how to deal with. From the point of view of PDE or analysis, these are singularly perturbed problems that tell me something about the regularity of that problem. By the way, I'm not assuming here that f is compatible. F can be anything, okay? It doesn't have to vanish at the boundary. We don't really know the extent of this connection with the theory of the continuous problem. I believe that there is a connection between this and Laplacian formula that I will talk about tomorrow, but I'm not sure. Anyway, we use this for numerics to compute, and we use this for some theory that I'm going to describe in a moment. Okay. Now, we do this, this is a transparency that is a complement of what I said. If you have these formulas here, now these are continuous, okay? The UI are functions in H10. If you discretize this with some finite element space in X prime, which I call SQ0, functions that are continuous polynomials of degree less or equal q, you get this quantity, okay, which is now a polynomial, piecewise polynomial, and then you get a fully discrete problem as a sequence of these problems in Y. That's what I just said before. Okay, by the way, the solution of this problem, semi-discrete, and the capital U are close exponentially in terms of the number of the number of elements we use to partition the Y interval. Okay, so now quickly, let me mention a few possibilities. The first one is, we call it tensor P1 finite element. So now I'm taking functions that are in L2 and a polygonal domain. It doesn't have to be convex. If the domain is not convex, we know that in the classical theory there are singularities at the reentrant corners. So if I want to compensate, I need a refinement in Y now, on the base. Okay. So the regularity can be measured for the Laplacian in weight spaces with these weights. This is standard. So we want to use this in our setting. So what we do, let me just go to the result, is we have a radical mesh in Y. Here is the way the mesh is in the variable, in the extended variable. We have a suitable mesh, a refinement towards corners in X prime. You combine them and you get this result for the solution of the fractional Laplacian and the trace of the solution of this combined problem. Refinement in Y, radical towards 0, and towards the corners of the domain. I'm not giving you the detail, this is technical, okay? But you believe me that you can refine the domain towards corners with recipes that come from Laplace theory, the second order theory. This is optimal in the sense that I mentioned earlier, degree, regularity, and rate of convergence, but it's not optimal in terms of degrees of freedom. It's the same problem I had before. I wanted this to be 1, not to be 3/2. Now I'm in 2 dimensions, as you see, so this was 1 over d, became 1/2 now because I'm in 2 dimensions. So I want to improve on this. We already improved with respect to the previous result, by the way, because now we do not have the domain to be convex. But we compensate with refinement towards the corners. So how do we get around this? There are different ways. One is a sparse grid approximation. And it's sort of, let me look at this. Here you have the space now in X prime times Y, in the cylinder. We have the regular finite element space of degree 1, and elements of and a finite element space of degree 1 in the Y variable. Okay? But look at the levels of refinement that I have. The sum of the levels of refinement cannot exceed capital L. L is the largest refinement level. So what this means in practice is the following. So you have small elements in Y, okay, maybe towards 0, and also small elements in Y, in X prime. And if you have a small element in Y, you want it to do a tensor product with a big element in X. Because if you have a small element in Y, you already have a small approximation, a small error due to that size in Y. You don't need a small element in Y, in X. And if you have a small element in X, you don't need a small element in Y. You can have a large element in Y. So you avoid, in your tensor product mesh, to have small in Y times small in x. And if you look at the y, you get a lot of degrees of freedom. It's because of these elements that do not contribute too much. Because if you have an element small in one direction, it's already good in terms of decreasing the error. So that you implement by saying that the sum of the levels cannot exceed a certain value. You put it together, you get a still linear order of convergence, but your complexity now is linear up to a log, okay? So we go from 1 plus 1/2 to 1 power, up to a log. Now this is quasi-optimal in terms of complexity. You can do HP in Y, meaning now you do a polynomial approximation that increases the polynomial degree. Let me explain what I mean. You start at Y equal to 0, and you have a mesh. The mesh is geometric. Okay? So the first element is small, the second element is twice the first element, the third element is twice the second element, and so on. You grow geometrically. And you look at the functions that are in these cells. They are going to be globally continuous, but the polynomial degree grows. In the first cell, you have polynomial degree 1. In the second cell, you have polynomial degree 2. And then 3. So you grow linearly from 1. Okay? If you do that, this is called an HP method. It has to be designed carefully. But then you get, again, linear rate and optimal complexity. You see the number of degrees of freedom that I have, the total number, is scaled linearly with the degrees of freedom in the x variable. Okay, this has to be done. Okay, the details we have in a very recent paper that you can find in arXiv, submitted 1 month ago. And also, we can even get better than that, it provided that the domain, which for the moment was polyhedral, is a good domain. If the domain is analytic, like a sphere, then you can have elements, you can have a decomposition of the domain that come back to Luis' question yesterday, that elements close to the boundary of the domain are long and thin. To capture the singularity d to the s, d to the 2s that we have in this case, without any compatibility of data. So long elements, okay, that are very thin. You have to tune the aspect ratio, how you go in one direction with respect to the other. Once you do that, that requires some analysis, you get exponential convergence in terms of degrees of freedom. So we go from order h to exponential convergence. Okay? So how am I doing with time? Do I have 5 more minutes? Maybe. I'm a little bit at borderline. Huh? Yes? That way I can conclude. This is not long. But anyway, maybe I should probably show you this picture before I move to the other topic. Here you have the tensor grid that has, in terms of degrees of freedom, a certain decay. It was n to the. If you express it in terms of degrees of freedom, you see it's worse than if you use HP or sparse grids that have a much better decay. So you do gain by doing this. Okay, the complexity is better, but of course it's a more complicated analysis. The methods are more complicated, and the only way you can do this is by understanding the structure of a problem. So the regularity of the solution comes in. For instance, for the HP method, we use all these analyticity results that I mentioned earlier. You go in Y, continue computing derivatives in Y and see how they behave. Because that tells us about the analytic behavior of the solution in Y. And Y, a mesh that is graded geometrically with polynomial degree increasing linearly, is the right thing to do. Okay? This is not just putting things together. It requires the analysis of the regularity of the problem. And now, a few words about the a posteriori analysis. As it happened yesterday, the idea is to have a dual approach. Everything I did so far expresses the error, the decay, in terms of regularity of the true solution. Okay? Maybe in a more clever or less clever way, exploiting analyticity or not, you get different results. This allows me to compare methods, okay, and say I improved with respect to the original method 2015. But it's not quantitative. I cannot say that I have a good result for a particular mesh, because it involves regularity of the function u, which I don't know. I know it exists, but I have no idea whether the quantities at hand are small or not. It's not quantitative. If I want to be quantitative, I have to go and do it a posteriori, namely using the discrete solution. And if I'm happy, I stop. If I'm not happy, I do something. I refine somewhere. I increase the polynomial degree. So there is a merit for this. And there is a merit for the previous approach. The previous approach is important because I show you a few methods and I compare them. And now I want to be quantitative. Okay. The first thing that we know about posteriori analysis is that you integrate by parts and look at the residual in a strong form. And use the residual in strong form to do something. If you integrate by parts, the weak form, you get this. Okay? This is the integration that comes from. But you see the weight y to the alpha in the boundary of the domain. Now imagine that the domain T is touching the bottom, in which case y to the alpha can be either 0 or infinite, or is close to the bottom, in which case can be close to 0 or blowing up. It's worse. So this formula here doesn't make any sense. Forget about the residual. You cannot even use it. It doesn't make sense. You have to go and you have to do it another way. And the way we have done this is by looking at alternative estimators, in particular local problems, which is what we design. Let me go to that immediately. So here's how the situation looks like. Imagine that you have a star, a hat function in the bottom of the domain. Okay? You know the support is like this hexagon that I mentioned yesterday. And by this cylinder, I mean the hexagon you multiply by the interval 0, y. Okay? So it's a cylinder. The bottom of the cylinder is the support of the basis function. These we call cylindrical stars. Okay, the star is called S z prime, and then I multiply by 0, y. So that's what's depicted sort of here. And then what I do is I solve local problems on these cylinders. Okay? Perhaps it's better to look at this. I'll remind you about the cylinder. It's called a z of z prime is the support times 0, y. I define a space there, and then I look at a local problem. Here is the local problem, where I solve for an auxiliary function eta z prime, and I put on the right hand side the residual of the equations. Here is the true solution, but without integration by parts. This is the residual written in weak form, which makes sense. Okay? Given this function, I compute the energy, and I collect all these energies. Okay? And this is an estimator. This estimator happens to be, I happen to have a lower bound, local, and an upper bound here, you see. So this does the job. Well, this is good news. We don't need to use the residual. The bad news is that this space here is non-computable. This is an infinite dimensional space. So somehow I need to discretize this. And when you discretize this, some problems arise. We have versions of the computable estimator, but not a complete theory. Okay? There are issues that have to do with so-called saturation assumption, saturation properties. If anybody